Hello, class. All right, so we're going to go over the last lecture in this first section of the class. So, last lecture on thermodynamics. And we're going to talk about something called entropy, and then we'll finish up with the third law of thermodynamics. All right, so we're going to look at kind of a concrete example of an engine. So say we have a hot reservoir that is at 400 Kelvin and a cold reservoir at 100 Kelvin. So we have some engine operating between these two temperatures, and let's say we're going to take 1,000 joules out of the hot reservoir. So QH is 1,000 joules. And yeah, so just in general for an engine, first law of thermodynamics and the efficiency of the engine. Okay, so what we're going to do is we're going to start out by looking at a Kernel engine. Okay, so for a Kernel engine, we look at the efficiency of the engine, where we have 1 minus QC over QH. Well, for a Kernel engine, that would be 1 over TC over TH. So again, just that relation about the ratio of heat to temperatures for a Kernel engine. So this would give us an efficiency of 75%. TC over TH, that's 100 over 400, or 0.25. So the efficiency of this engine is 75%. And then we can use that to find QC. We know QH. We can find QC from this as well. Because, let's see, QC over QH equals TC over TH. So QC would be QH, which is 1,000 joules, times TC over TH, well, 0.25. So QC would be 250 joules. So again, that's for this Kernel engine. Now, what I want to do is calculate, I'm going to erase this. So here, for our Kernel engine, QH is 1,000 joules, and we found QC in this case would be 250 joules. And what I want to do is calculate QH over TH plus QC over TC. Now, notice I did not put absolute values on this. Normally we put absolute values on the Q and the heats, but in this case we actually want to look at the direction it's going. Well, we know what direction it's going. We want to take into account the plus and minus though. So QH, we're taking heat out of the hot reservoir. So QH is going to be negative. So this quantity, we're going to have minus 1,000 joules. And it's out of a temperature, 400 Kelvin. And then QC, and we're adding the second term, where QC was 250 joules. We divide by TC, which is 100 Kelvin. So we're calculating this quantity. And again, why are we doing this? Well, we're going to do it a few times and just see the result of it. Okay. Now, again, it's easy to see that this is going to give us 0. If you just multiply the top and bottom by 4, 250 times 4 is 1,000. 100 times 4 is 400. Just get a common denominator. And so this quantity is 0. So what we're calculating, I'm going to leave this up here. We're just going to keep calculating that. So we did this for a Kernel Engine, and the result is we get 0. Let's look at a more realistic engine, though. Kernel Engine, something with the efficiency of a Kernel Engine, extremely difficult to actually build. Probably impossible to get it exactly right, but we can get fairly close to it. Okay, so let's look at a real engine. So let's see. Let's say we have an engine with an efficiency of 50%. So again, the Kernel Engine at these temperatures has an efficiency of 75%. So an engine with an efficiency of 50%, definitely a very possible thing that we could build. And so we can calculate, we know QH is going to be 1,000 joules just like before. Now let's calculate QC. So here we have efficiency is 1 minus, so our efficiency is 0.5. That would be 1 minus QC over QH. So QC over 1,000. Well, 1,000 joules. Okay, so QC over 1,000 joules. That would be 0.5. So QC would be 500 joules. Just put that here. And once we know the efficiency and we know QH, we can find QC. And we just did. So for an efficiency of 0.5, QC would be 500 joules. And so we're going to calculate this same thing that we did here. We don't have a name for it yet. But we have QH over TH. Plus QC. And again, no absolute values. We're going to do this. So we have minus 1,000 joules divided by 400 Kelvin. And then QC is 500 joules divided by 100. Sorry, Kelvin, not joules. Okay, so to get a common denominator, 4 over 4. So we'd have minus 1,000 plus 2,000. So that'd be 1,000 joules over 400 Kelvin. So again, we're getting a common denominator of 400. And so we multiply this by 4, that'd be 2,000 minus 1,000. And again, this is just 2.5 joules per Kelvin. Okay, so what we had for our real engine, here we have 250 here. We had this, let's just call this sigma for right now, because it's a sum. So here we had sigma equals 0 for our Kernel engine. For our real engine, we ended up with the sigma. It's a number, but it's greater than 0. That's the important thing. Now, let's consider an imaginary engine. Let's say we have an, what should we call this, a fake engine? Let's call it imaginary. Or an impossible engine. Yeah, let's go with impossible. And the reason why this is an impossible engine is we're going to say that this engine has an efficiency greater than a kernel engine. I think I use 90%. Yeah. So let's say the efficiency is 90%, or 0.90. Now again, the kernel engine, the efficiency was 75%. And we know that's the most efficient possible. So if we could build an engine with an efficiency of 90%, let's calculate QC. So QC over QH. If we had to solve for that, that would be 1 minus E. So that, in this case, that would be 0.1, which would mean QC would be 0.1 times QH, which was 1,000, so that would be 100 joules. So again, we're not dumping too much into the cold reservoir here. So let's calculate this sigma again. We'll give it a different name later, but so we have QH over TH, and remember QH is negative. So we have minus 1,000 joules over 400 Kelvin. And then plus 100 joules over 100 Kelvin. And so again, if we get a common denominator of 400 Kelvin, we multiply that. So that's 400 minus 1,000. This would be minus 600 joules. So this is what, minus 1.5. And the key here is that negative sign. So for a kernel engine, we have the sum sigma. We're calculating the sum here. And what we end up for a kernel engine is 0. For a real engine, we get something greater than 0. And for this impossible engine, if we had built an engine that is more efficient than a kernel engine, this sum would be less than 0. But again, this is impossible. So for all real engines, we're going to get the result that sigma is going to be greater than or equal to 0. So, yeah, I'm going to erase everything now. Those numbers, I think, just make things easier to see. But basically, for any real process, we have what we're right now just calling sigma has got to be greater than or equal to 0. It can never be less than 0. And so, and it turns out this equal sign that's only possible for a reversible process. So if you have an irreversible process, this sum is going to be greater than 0. A reversible process, that's where the system and its environment can be brought back to its initial state. So you have some change, you go through some process, but you can return the system and its environment to its initial state, then the sum is 0. For any other process, the sum is greater than 0. And so we're going to find something called entropy. We use the letter S for entropy. And it's measured, the basic SI units are joules over kelvins. Now, entropy depends on the state of a system. So what we're looking at is changes, but entropy itself only depends on the state of a system, and it's actually possible to define the entropy of a system, like to give a definition of how you could calculate it. But we're not going to do that in this class. What we're going to do is just, we can define the change in entropy. That's equal to the sum. We're going to write it this way. And the reason why, we only have two parts to our system, like a hot reservoir and a cold reservoir, but in general, your system can have more parts to it. And so here, what we find is, ultimately, this is based on the second law of thermodynamics. The result we found is that just universal, here, now we can just replace sigma with delta S, change in entropy. So, let me redo that. So the change in entropy, so we had QH over TH plus QC over TC. So again, we're just defining the change in entropy this way. And actually, this is how entropy was first defined, by discussing changes in entropy. Later on, it was shown by Boltzmann. We've heard of him before. He actually showed a way where we can define entropy as just a part of the system. And it's based on statistics. The basic idea, I'll discuss it very briefly. Maybe an analogy would be better. But the idea behind entropy is, if we look at the exact, like say we have a gas. I'll start out with like a real example. And so to really define this gas precisely, you would need to know, like it'd be enough to know, say, the position and momentum of every particle of the gas. So you've got this, for practical purposes, this uncountable number of molecules. And if you know everything about those molecules, like the velocity and, the direction, mass, and like where they all are, we can completely define the gas. But more practically, we define things like pressure and volume and temperature. And the idea is, kind of the fundamental idea here, and let's say we have a gas with a temperature of some value, like 300 Kelvin. There's a lot of different ways that this could happen. You look at the molecules, like if I tell you the temperature of this gas is 300 Kelvin, you don't know, that doesn't tell you what's going on inside the gas. There's a countless number of ways that could be achieved. If we look at the actual motion of the molecules, there's countless ways that you could come up with a gas with a temperature of 300 Kelvin. And entropy is based on, for these observable properties like temperature, pressure, if we define the gas in terms of these observable properties, we call those like the macro state, the large scale behavior. Things like temperature and pressure. If you look at all the ways that could happen, that would be related to the entropy of the gas. Now, it's kind of, maybe it'd be better to look at an analogy. So we have these two ideas. We have the macro state. This would be like, say, pressure, temperature, volume, the things we use to describe the state of a gas. And the micro state would be the detailed description. Of everything that's going on in the gas. Like the mass, velocity, position of every molecule in the gas. And again, it's very hard to wrap your mind around that because it's, the number of molecules of gas is literally more than you could count in your lifetime. The idea that we could even know what it would be, it's impossible. So I like this kind of analogy. Let's keep a really simple example. Let's say we roll 2 dice. And we're going to take the sum. So the macro state, in this case, the possible macro states would be 2, 3, 4, all the way up to 12. So these are the macro states. Now the micro states would be, like, let's say for a particular macro state, let's say 4. Let's say the macro state is 4. What micro states could give us this result? Well, we could have 1 and 3, 2 and 2, and 3 and 1. So these are the micro states. And basically there's 3 micro states that will give us this macro state. Now if we look at a different example, well, there'd be 6 micro states that would give us the macro state of 7. You could have 1 plus 6, 2 plus 5, all the way down to 6 plus 1. And the idea is that the entropy is a function of how many macro states, or how many micro states there are for a given macro state. Precisely, the entropy would be proportional to the natural logarithm of, let's just call it m, lowercase m, I guess, for micro states. So that's a natural log of that. So again, it's very easy to see if your macro states are the sum of 2 dice, and the micro states are, die 1 is this, die 2 is that. You can imagine 3 dice as well. So you'd have numbers up from 3 to 18. And again, this kind of relates to this idea of entropy. Let's say we have 2 dice in a box, and we shake the box, and so the dice are going to be scrambled. And if we look at, if then we open up the box and look inside, what are we more likely to see, 4 or 7? We're more likely to see 7 than 4, because there's more microstate. Like, every microstate is equally likely, so just because there's more options here. Now, would you be shocked to find 4? Not at all. We can look at an example if we have 2 dice. Let's say we shake it and we open it up and there's the number 7. And then we close the box, shake it again, open it up, and then we see the macro state 4. Are you going to be shocked that we went from this more probable state to a less probable state? No. And the reason why is because there's only 2 dice. But what if we had, say, 1 billion dice in a box, and we shook it up and averaged, or let's say a different example, we look at the average instead of just adding them all up. If we took the average of all those dice, we should expect around 3.5 billion. And again, that would give us the, there'd be the most microstates would give us that average. And getting a less likely macro state, like say getting an average of 1. So we have 1 billion dice in a box. Imagine we shook up the box, opened it up, and we added all the dice, and we got 1 as an average. Now, the only possible way that can happen is if every die was a 1. That's, otherwise the average would be higher. If even 1 die was higher than 1, then the average would be more than 1. Now, is it possible that that could happen? Yeah. What are the odds of that happening? That'd be, 1/6 to like the billionth power. So again, you could shake those dice all you want, keep looking inside, you're never going to actually get that result. And again, this idea, the number of microstates that correspond to any macro state, that's related to the entropy. So again, if we go to this example, if we go back to that, initially we have a 7, and then we shake up the box and get a 4, that would be like a reverse of entropy. We went from a likely state to a less likely state. But again, if we had 1 billion dice, it's possible that that result could happen. That we'd have something around 3.5, and then we shake it and open it up and take the average again, and we get something like closer to 1. That is possible, but it's extraordinarily unlikely to happen. And that's kind of the fundamental idea of entropy, it's not a fundamental law like the universe requires that this to happen. It's statistics that require this to happen. So it's possible, theoretically, that the entropy of a system could spontaneously reverse. But again, in the actual real world, that just does not happen. For any macroscopic system, even if you look at just say a cubic centimeter box, and you look at the air in that, the odds of entropy reversing inside that, it cannot happen. Theoretically it can, but it never will. So again, this whole idea of entropy, it is based purely on statistics. But what we found is that, now let's go back to this example again. Let's go back to that box with, say, 1 billion dice in it, and say we set it up so initially all the dice are 1 and our average value is 1. Now, it's very easy to get to that average of 3.5 or something close to that by just shaking the box. So it's possible for a system to exist in a very low entropy state. That would be like every die is 1. It's a very ordered thing. And a very unlikely result to occur randomly, but it could be set up that way. And so, it's possible for a state to be there, but it's very easy to leave that very ordered state. Just shake the box, and you'll go from a very ordered state to a very disordered state. The reverse process, that's virtually impossible. If you say the dice are in one of the countless ways that they could average to 3.5, if you shook the box, open it up, the odds of getting an average of 1, it's just never ever going to happen. There's only one state where the average value is going to be 1, or even if you look at things like unusual averages, like say the average should be 3.5 if we're looking at ordinary dice. So to get an average of say 2, again, it's extremely unlikely. The larger the system, the more unlikely the result will be. And so, we can basically treat this as just a true law of the universe, even though it's based on statistics, just because these odds are so enormous. Now, there is one thing where we might want to consider entropy being reversed. Because they came up with this stuff in the 1800s. Now, I'm assuming that everyone's aware that at some point there was something called the Big Bang. It was around close to 15 billion years ago, when our universe was very tiny, and it went through this rapid expansion, and it's been expanding ever since. But in the 1800s, they didn't know that. The thinking at the time is that the universe was eternal and basically unchanging. And this idea of entropy, when they came up with that, that was a real problem for them. Because as the universe evolves, it has to go in one direction. It can only go in the direction of increasing entropy. And a process, we're talking about changes, like any process. Anytime there's a change in the universe, it can only go in one direction, statistically speaking. And that can be kind of bad news in a sense, because in order for anything to happen, we have to have a process. You need, basically any realistic process, the entropy has to increase. And what if it kind of reaches this maximum value where no further change is possible? That's kind of seen as one possible end result for our universe, is that the entropy will keep on increasing until no further change is possible. There could be like a maximum value of entropy where any change from that state would be impossible, because if you're in a maximum state, to move away from that, you'd have to decrease the entropy, which cannot be done. And so when they came up with this in the 1800s, that really made this idea of an eternal universe very problematic. Because, how can you have something that's evolving in one direction and be eternal? And the solution that they came up with is that this is actually just based on statistics. So it's possible for the entropy of a system to spontaneously reverse, just improbable. And so thinking at the time was that the normal state of the universe was just its completely natural state of maximum entropy, where absolutely nothing is happening. Like, just for example, like say a star is burning. That's increasing the entropy of the universe. So we cannot have, life is another example of very organized behavior. And so, again, like low entropy. So like anything interesting going on that involves kind of this organization and a low entropy state. So the thinking at the time was that the universe was just normally in this maximum entropy and very boring state. However, because they believed the universe was eternal, that, remember like the odds, like say again, you have a billion dice and you shake up the box, it's possible you could open up the box and just see all ones. So, but that's so extraordinarily unlikely, you would never see that result in any realistic finite time span. But if you had an eternity to keep shaking up that box and looking inside, eventually it's bound to happen. And so that's what they thought, like why our universe is an active place is that, it probably spent just countless eons in this kind of boring maximum entropy state, and then just through this incredibly improbable event, the universe just spontaneously jumped down into a lower entropy state, and then it's going to go back to maximum entropy and stay there for, many, many times the lifetime of the universe, at least as we know it now, the 14 or 15 billion years. Yeah, and if we reach maximum entropy, the odds, like to jump down into like a kind of universe we see now, 14 billion years wouldn't even come close to covering something like that. It would have to be so long that it's unimaginable, really. But again, they believe the universe was eternal, so even the most improbable event could happen if you wait long enough. But now we know our universe, we don't know what the Big Bang was. We really don't know. Thinking now, and again, it's mostly guesses, but not completely guesses, but ideas that have not been fully worked out. But they actually think something caused our Big Bang. So there was something before the Big Bang, but let's just say our universe started at the Big Bang. So there was something that caused that to happen. But yeah, we've still got some time left. We're still in a relatively low entropy state. But eventually, all the stars are going to burn out. Everything's going to be the same temperature eventually. Yes, entropy, it's like a one-way evolution. And I don't want to talk more about like what's going to happen in the future because we don't know. Like, is the universe going to keep expanding forever? Or is it going to slow down and come back? We don't know these things, so I don't want to speculate too much on that. But yeah, this is kind of like a one way that we're going. The evolution evolves in the direction of maximum entropy. All right, now coming more down to earth. I want to just do one example of actually calculating an entropy change. And I'm going to do this, I'm going to make up a problem. Here, it's winter right now. So, I don't know what the temperature is, but let's say it's minus 4 degrees Celsius outside, which is probably not, too far off. So let's say inside the house it's 25 degrees Celsius, outside it's minus 4, and say in a certain time interval, a certain amount of heat is going to leave the house. Let's say 10,000 joules of heat is going to leave the house and go outside. So yeah, we talked about heat going through the walls with and without insulation. So yeah, heat's going to flow from hot to cold. So in some time interval, 10,000 joules. And I want to know the change of entropy of the universe as a result of that heat flowing out of the house. So I'm going to do this two ways. The first way I'm going to do this is incorrectly, and then we'll see what went wrong and fix it. So let's plug things in. Delta S, and again, we're going to do this wrong at first. So QH, that's the heat being removed from the interior of the house, so that's going to be negative 10,000 joules. And then we divide by TH, which is 25 degrees Celsius. And then we're going to add 10,000 joules divided by the temperature outside. So again, the heat is entering the outside. So QC is positive, and that's at a temperature of -4 degrees Celsius. And so both these terms are negative. You know what, I'm going to change this number. Let's make things a little bit easier. Let's just change this by 1 degree. So we can just multiply this by 6 to get a common denominator. Okay, so we have a common denominator of 24 degrees Celsius. So here we had 6 times 10 to the 4th minus 1. So if we do this calculation, we get minus 5 times 10 to the 4th joules over 24 Celsius degrees. And we see that the change in entropy of the universe was negative. Now, we just said that's not supposed to happen. So what actually did happen here, and I made a very common mistake, which is why I did this on purpose. The temperatures in this equation must be in Kelvin. And so I plugged in the numbers in Celsius, and so that is completely wrong. And so it should have been a hint that we got a negative, because, again, this is a spontaneous process. Heat going from hot to cold, that's an irreversible process. You wouldn't expect that heat to just flow back into the house. Now, you can add heat to the house by expending energy, but it's not going to just flow from outside to inside. So this is a reversible process, and let's kind of summarize here. Delta S. So this is greater than 0 for an irreversible process. Or it's equals 0 for a reversible process. And it's less than 0 for, let's just say an incredibly improbable process. And then in parentheses, impossible. Like, realistically speaking, delta S is never going to be less than 0. If we look, and again, we're looking at an overall change in entropy for the universe. It is accurate to say that the universe can be like your house and everything outside your house. That covers everything. Now, if you look at, let's fix this. We did this wrong, or I did this wrong. So let's fix it and put in the right numbers. So again, this is 274. We have to add, 24 degrees. Remember, the offset is 273 to convert to Kelvin. So this would be 297 Kelvin. And this would be 269 Kelvin. So if we plug these numbers in, we have, this was TH 273, and this is 269. Now, out of these two numbers, this one is bigger in absolute value. I mean, it's not just bigger because it's positive and this term is negative. Forget the minus sign here. They have the same numerator, so if you have a smaller denominator, that's a bigger number overall. Like, say you have $100, but you have to share that with everyone in the group. Do you want to be in a group with 10 people or 3 people? You have more money if you're in a group of smaller people. You're dividing it by a smaller number. So, this is a bigger number, and so I don't care what this number is. The end result is the change in entropy overall is greater than 0. This is an irreversible process. And again, you really want to check and make sure that the temperature is in Kelvin in order to make this work. Well, I mean, it just has to be that case. Now, I said this is like the overall change in entropy in the universe. If you look at the change in entropy of the house, that is negative. So it's possible to have a local decrease in entropy. Yeah, when you take into account the environment around it, then the change is always going to be positive. And again, so it is important to know that entropy can be reduced locally. It says universally it has to be greater than 0. When they came up with this was actually used, this idea of entropy was used by some to try and discredit natural evolution. Because evolution, life started out very simply. We don't even know how life started out exactly, but we do know that it started out as just like things like bacteria, just like very simple single-celled organisms, and then it grows more complicated over time. And kind of loosely speaking, entropy can be seen as a measure of like how much disorder there is. So like the evolution of life, like the formation of life and the evolution of life, that's going against entropy. But that does not violate any of these laws, because overall, we have this constant supply of energy from the sun. Like say the sun disappeared tomorrow. What's going to happen to life on this planet? We would all die in a fairly short time. All life on the planet would die. Actually, that's not even true. I don't know. There are some creatures that live in the ocean near hydrothermal vents that don't seem to depend on the sun at all. Because we have a source of geothermal energy which is still based on the Earth not having been cooled down completely and kind of sustained by radioactive decay. So not everything depends on the sun, but other than that, like all the vegetation would die, there goes our food chain. Basically, just about all life on the planet would die and decay. And so, yeah, like the entropy of life would decrease very rapidly if we didn't have this outside source of energy feeding us, mainly sunlight. And again, stars burning, that's a huge creation of entropy there. That's where like most of the entropy of the universe seems to increase, just the process of stars, going through their nuclear reaction and converting that energy, just kind of, what they're doing is they're converting mass into radiant energy. And that's a huge positive delta S there. And so, yeah, that's why, locally speaking, entropy can be reversed, but it depends on entropy being increased somewhere else, like in this case, the sun. So yeah, overall, you think the universe is kind of going downhill. We're running out of useful work. Okay. And yeah, entropy, this is a subject, we could keep talking about this forever, but I think we'll stop here. And the final thing I want to talk about, just for completion, even though I already mentioned it, the third law of thermodynamics. And I'll read what that says. It is not possible to lower the temperature of any system to absolute zero in a finite number of steps. And again, it's kind of a simple concept. Well, I'll just kind of go over that basic concept again. Let's say we have an object at a particular, say, reasonable temperature, like, say we're at 300 Kelvin. And let's say we remove 1,000 joules of energy, we're going to get some delta T. And maybe a fairly significant delta T. But again, in order to remove that energy, we have to do some work. So, yeah, maybe, here, let's just say we remove some heat Q. So let's say we do 1,000 joules of work to remove some amount of heat. And again, remember, this energy never disappears, so we have to take heat out of this system, which is at room temperature, and put it in the room. That's not that difficult to do. So we can do that. But now the temperature has decreased a little bit. So let's say we use an additional 1,000 joules of energy to lower the temperature more. Well, now this object is a little colder than the room. And so to reduce the temperature more, it's a little bit harder this time. So if we apply the same amount of work, we'll get a smaller delta T. Maybe not much, but as we keep going through this process, we're looking at finite steps. We move 1,000 joules of energy at a time, and we get these diminished returns. Our goal is to get these temperature decreases. And so initially we're making great progress, but it gets harder and harder to do. So if we keep doing this like 1,000 joules, temperature change is going to keep decreasing. And yeah, like I said, in any finite number of steps, we're never going to reach absolute zero. So that's a basic idea behind the third law of thermodynamics. Absolute zero represents kind of like the lowest temperature you can achieve. For something that's a positive temperature, you know, you can lower it and lower and lower it. You can never actually reach absolute zero, though. They can get extremely close to it, like, you know, 0.000 something Kelvin, but you can't actually reach absolute zero. So that's it for thermodynamics then. So we covered 4 chapters in the book, chapters 12 to 15, and yeah, then next we're going on to a completely new section. So, all right, that'll be all for this section then.